were some issues with the 2 review sessions that we had for lecture, so I just wanted to record the new topics that were covered, or the relatively new topics that haven't been done in the previous reviews, just so that we can have an idea of those. And then I want to go over the last 2 things that were unrelated to the exam, just so that everybody is aware of them at least. Before we get started with the review, if you haven't already seen the announcement on Canvas, please, if you could, go take this ABET assessment that's available in the quizzes section. It's not for a grade, and it's relatively short. It's all multiple choice. It's an assessment for the university so that they can know that we're actually teaching the material and so that the university can stay certified. So if you could, please go take that. It's standard for engineering classes if you haven't done it before, during spring and fall. So you can expect to take a lot of these if you are an engineering major. And then just a reminder that the actual final exam is on Tuesday, December 7th. I'm leaving it open from 4 to 10, so if you need more time to study, or if you want to take it earlier on, you have the option to. It should take about 2 hours to complete, which is the normal UNLV scheduled time for the exam. You have a little bit of extra time there just in case you need to submit things or you're having technical issues, then there's some extra time just to have some leeway. Anyways, let's go ahead and get into the review material. So the 2 things I mainly wanted to talk about were linked lists and then stacks and queues, which were the 2 things that weren't on the previous 2 midterms that will be on the final. As a reminder, it's cumulative, so it will cover everything. So I recommend going back and rewatching the first review and the second review if you need to see those, because just for the sake of time and not having to re-record all of the material, since it did take about 3 hours, I'm just going to do linked lists and stacks and queues. Now, as a reminder, a linked list was a set of these things we called nodes. So we had the idea of a node, which we've generally been declaring as a struct. And the node can take a bunch of different variations, but the main thing that we had with it were 2 fields. One, which was the data field. So let's mark this as a template in our code, just so that we can make the data anything we want. Last T. And this was just something that stored some kind of data. Similar to how you would put things into an array, this is just the type of things that the linked list or whatever data type or data structure that we're doing is going to be holding. And then it had another aspect to it, which was a pointer to another node, which is called next, is the way we normally called it, or the link, just some sort of pointer that points to another node. You can have things on top of this. You can have extra pointers, or you can have more information if you're going to store something in particular inside your node. But this is the basic setup and the 2 things that we at least expect all types of nodes in any sort of our data structures that take a linked fashion to have. The first main type of linked list that we covered chained these nodes together, these singly linked nodes that just have a data field and a pointer to some other node. Right? So generally we've been representing it this way, where the first part here holds the data, and then the second part is the link or the next pointer, which points to another node in the structure. As far as our linked list implementation goes, for our singly linked list, we only have 1 pointer per node, hence the singly linked part, and we basically just chain together these nodes so that they store data and we eventually reach some end. And the way we denoted the end was with this symbol, or if we wanted to write it as an actual value, it was null, being null or null pointer in C++, represented by the null symbol there. Right, so the way we represented this is if we're at the end, then the last thing is pointing to no other node, i.e. null, which represents nothing when we're dealing with pointers. And the other thing that we kept when we were doing linked lists was a pointer to the head. Where does the list start, and how can we get there so that we can actually traverse through the list, right? And again, we could keep some other pointers if we want to make things easier for specific operations, but this was just our general setup for a singly linked list. And then remember, the way we had to traverse these was we would start at the head every single time because it's the only pointer we kept in our default implementation of a linked list. And if I wanted to access something, I would need to go further on. So let's say this is data 0, data 1, and data 2. Then if I want to access whatever this thing is that's being stored here, data 2, if we were having this be a list of numbers, maybe this is like the number 3, 4, and 7. If I wanted to access that integer 7, I would have to start at the head, follow this, follow that, and end up at that 7. So I have to always start at the head and traverse as far as necessary to find the thing. This was different compared to an array, in that we can't just jump straight to our location. So with an array, and the way we would store these data points would be data 0, data 1, and data 2, where those indices are also the indices into the array, position 0, 1, and 2. And so if I wanted to go and grab that thing, data 2, in an array, all I have to do is access that array with that specific number, right? I can go array sub 2, and when it goes and accesses it, it quite literally just jumps straight there because it can do that with math because these things are right next to each other in memory. Therefore, we can just add some amount of skips, like how many data are before it from the beginning of the array to just get straight to it. So the main difference between an array and a singly linked list, if we kind of compare and contrast them. So this one, everything is contiguous. When we do an array, right, at least a single dimension array, everything is stored directly right next to each other. Whereas when we do things in a linked list, it is discontiguous, meaning they're not all right next to each other. They could be potentially, but because of the pointer, we're assuming that they could just jump around in memory and be located anyway, or anywhere. So that's a good thing for an array because the lookup is easy and fast. Whereas in a linked list, because they're not all connected, they're discontiguous, we have to look through the whole thing potentially, or at least start at the beginning of the thing. Right? We always have to start at the head and work our way through unless we keep other pointers, but it's still not just something where we can jump straight there. It's some sort of linear search if we need to get something out of our singly linked list. Right? So that's one advantage of using an array over using a linked list. However, because this is contiguous and because this is discontiguous, there's also an advantage for a linked list versus a array, which is that if this runs out of room, then we have to go and reallocate space, right? Say I already have these 3 things in my array, and I go and need to add a 4th thing to the end of this, some data point 3. I can't just go write that to the end of the array after D2 because it may be memory that's being used by something else, and on top of that, it may get overwritten because the operating system is not expecting us to use that memory because it's not part of our array. And generally, the runtime environment in C++ is going to stop you from doing that anyways and tell you it's a sig fault. So we can't just go out of bounds of the array. We have to make a bigger one, copy everything over, and then put that stuff in there, and then we have more space to put things in. And that happens every time we run out of space in an array. So if you're expecting there to be a kind of like online data where you're receiving more and more data over the course of your program, then an array is sometimes not the best choice. However, if you're expecting there to be a static amount or a cap at least on the amount of data that you're receiving, then an array is probably a good choice. consider that an array is faster for its lookup, but it gets some slowdown if you have to resize it compared to a singly linked list where it never has to do that copying because of the way it works, right? It always makes one new node and throws something at the end, meaning that we always can go and just make more space because they don't have to be right next to each other in order to access it. Right, so this allocates just one every time. Which means the allocation is going to be spread across the program rather than just all at once when we allocate the single array. So the allocation is potentially slower if you never reallocate the array, but we get some speed out of it potentially, and it's just easier for the memory to be allocated, right? In terms of flexibility, at least. Right? So that's our advantage of using a linked list and why we might use it. And then I think that would be the main advantages and disadvantages of these two things, right? So the traversal in a linked list is slow, whereas it's very fast in an array, but the memory, the way it's done, it's bad if you run out of space in an array, but in a linked list, you don't really have to worry about running out of space. Now, again, you should always try to use an array if possible. If you know you're not going to have to constantly have that disadvantage, that resizing thing, then it's good for multiple reasons, because that lookup is fast, and also because of the way that an array is accessed. The hardware can actually do speedups on that, where it can't do that with a linked list, which we don't cover in this class, but just as something to keep in mind. So those were our differences between a linked list and why we may use this new data structure we had. And then let's just talk a little bit about some other types of linked lists. So we had the singly linked one, and then we had a doubly linked list as well. And the only difference between a singly linked list and a doubly linked list was just how many pointers we had. Right? So maybe I'll do 3 here. So we still keep some sort of data field, right? And we still keep the next pointer that we had, but we keep this one additional pointer. So I keep the pointers to the right that we normally do, and keep the end as null. And I keep my data in here, so this being data point 0, data point 1, and data point 2. And then the difference between a linked list, a doubly linked list, and a singly linked list was that it also had a pointer that went backwards on each node. So we changed the way that the nodes work so that it points both ways. And this was nice because we could do traversal in both directions. If there was ever a point where we needed to start from the middle of the list and work our way backwards, then now we have the ability to do that, which is useful for some data structures, but may not be for all. So it can be a little niche, but this is just a way to get around the shortcomings, or one of the main shortcomings of a singly linked list. Okay, and then the last major thing we had were circularly linked lists, which could be single or doubly linked. And all that meant was that once we get to the end of the linked list, rather than having it point to null, we have it point back to the beginning of the list. That way, again, if we ever need to start from the middle for whatever reason, then we can work our way back to the beginning as part of our traversal. This is kind of like the ring buffer that you may have done in assignment 7. However, we did it with an array there. This is a fairly easy implementation of it, where you can just automatically go back to the beginning of the thing by following the next pointer, and never have to worry about doing modulo if you, for whatever reason, don't want to do modulo. So just another kind of implementation for that kind of thing. It also works for doubly linked lists. The difference here would be that not only does the end point back to the beginning, but the beginning would point back to the end, both instead of null. Right? Since in a doubly linked list, both the beginning pointing left and the end pointing right are both going to be null. Okay, And so with a lot of data structures that we do, we have two main operations that we need to consider, which are the insert and then the lookup and the deletion. And for the sake of this, let's just do the insert and the deletion, since the lookup is essentially just the deletion without the delete part. So generally we keep a head, right? Head pointer. If we ever have an empty linked list, then the way we said we represent that is to simply have the head point to nothing, since there's nothing in our linked list. And this also helps us out for things like recursive implementations of linked list, since it allows us to have some sort of trivial case for linked list that represents when they have nothing in them. So by default, we say that the head is pointing to null, that there's nothing there. And then whenever we want to do an insert, what we do is we create a new node, store whatever data goes into it, set its pointer equal to null, and then we have one special case. So if there is no head yet, then we need to set the head. Right? So that was the one edge case we had for insertion in a linked list, was just if the head is empty, then we also need to set that head, because it's a special variable, right, that we keep inside the linked list class that is separate from anything else. Therefore, we need to set it if it's not set already. So on the first insert, we do that. On any subsequent insert, then we do the same thing every single time, which is essentially the same as the head insert, except we just don't need to set the head, which is we set some sort of new node, right? We make some new node. We have its pointer set to null, since it's not pointing to anything after it. We set its data field to whatever it is that we want to put into that data field, and then we make the last thing that was in the array, or sorry, in the linked list, point to that. So the previous n points to this one. So if I was to go and insert one more node, generally what I would do is I would start at the head, work my way until I reach to the end. So we start at the head, go through this D0 node, go through this D1 node. We know it's the end because its pointer is null. We would then make this new node, initialize its fields, and then simply make what we found to be the end from our traversal point to that new node, right? And then we continue to do that every single time. We can speed this up a little bit. So this was one of our main disadvantages of a linked list, is that the insert always takes a linear amount of time, because we always have to go from the start to the end of the list. And so we need to traverse through how many things are currently in the list to get to the end, which is kind of annoying and a little slow, and the main disadvantage of using a linked list, aside from that whole accessing part that we talked about. And so it's a common implementation to, on top of keeping a head, to also keep track of a tail that just represents where is the last thing in our linked list. That way we don't have to do a traversal every time. If we need to do an insert, we can just put the thing there. Okay, so if we now wanted to insert another node, let's just say we initialize its values. So we set its data field to whatever data point, data 3, and then make it point to null. What we would simply do is set the tails link, the tails next, to point to the new node we created, and then redirect the tail so that it goes and points to the new tail that we just created. So by adding a tail, you essentially just give yourself one extra operation, which is resetting the tail, but you make the traversal a lot faster. And this would be an example of where a singularly linked list may be useful, because of the fact that we're not starting at the beginning. If you, for some reason, started at the tail, you might want to link your way back. Same thing with a doubly linked list. This would also allow us to go a little bit backwards, which might be helpful if we know these are going to be in sorted order, let's just say. Okay, so the other one we had was a deletion or removal. And so, again, we have some special case, which is involving the head. So we have two special cases involving the head. One is kind of trivial, which is just if the list is already empty and we go and try to delete something, then we should probably not do that, because you can't delete anything from a empty list because there's nothing in it. The other special case we had was if we were deleting the head itself. Again, consider if we are deleting the head, and since that is a special variable, we need to set it whenever we do that. So if, let's just say we had this linked list already created with two data points, data 0 and data 1. Then if we wanted to go and delete this data 0 right here, what we'll need to do is keep some sort of temporary pointer to it, delete it. Actually, before we delete it, we need to redirect the head to be in the correct location. So we follow its link to say, okay, the head is now the thing that came after it. And then we deallocate it. Right? And then our temp is no longer needed. So just our one special case was if we needed to delete the head. Let's say we wanted to delete something that wasn't the head though. Let's add one more data here. Let's say we wanted to go through and delete data 1. And the way we would do this is we would start at the head, check for which one is data 1. So we start here. Is this data 1? No, it's not. Is this data 1? Yes, it is. So we need to delete that one. We traverse the list until we get to a point where the thing we need to do is needing to be done, which is the same thing as a lookup, right? Which is why we're kind of skipping that one. And the way we said it was easier to implement this was to keep two pointers, a pointer to the current node, the one we're looking to delete, as well as to the one previous to it. There are many implementations for this, but this was just the way that I thought was easiest and maybe simple to keep if you're just starting out with linked list. So what we did was we kept two pointers, one to the current, one to the previous, the one that comes before the one we want to delete. And then we said that if we just deleted the current one straight up, then this creates an issue because now the node coming before it, the one that's holding D0, is now going to be pointing to nothing because we deleted the thing that it's pointing to. Now we have a dangling pointer, and everything to the right of D1 is now lost because we're not pointing to it anymore. We got rid of the pointer to it when we deleted that node. So we said we need to do things in a little bit different of an order. The reason we needed to keep a previous was to make sure that this points to the other side instead, that it's not pointing to the thing we're about to get rid of. And then after that, we go and deallocate this thing. So we keep this previous so that we can redirect it to point to the thing that was next after the current pointer, and then we can delete it after that because it's safe to do so. The only difference between this and a singly and doubly linked list was the fact that if we were doing this in a doubly linked list, we would need to set both the previous one to point around it to the right and the back pointer for the one after the current one to point back to the previous node. So those were our two main operations, insert and delete for these. We had one special type of insert that we talked about as well, which was just if we wanted to do some sort of sorted insert, which you may have remembered from assignment 9. And the way we did this was we just simply looked at the things we were inserting after and stopped a little early if we were going to put things out of order. So say we have a linked list already created. Again, a trivial case of head being null is where we would just set the head and that would be easy to insert. But let's say we have something where it's a list of integers. And it looks like this. And the things that are being stored in this one are the numbers 3, 4, and 7. And we want to go and insert the number 5. But make sure that this stays sorted in order rather than just doing this in such a way that we always insert to the end, which is what we normally do, right, when we're inserting. Then what we do is we traverse as normal. We start at the head, and then we check, is it bigger than that thing? Or I guess we would rather check, is it less than that thing? So we would say, is 5 less than 3? No. Is 5 less than 4? No. Is 5 less than 7? Yes. Meaning we should insert it before that 7. So if we want to insert a node now with the 5 in it, we need to create it as normal. With our traversal, we would simply keep track of the current one that we're checking, as well as, again, a previous one. Make sure that we track what the last one we looked at is, because we're going to need to point to it. And then we simply make the previous point to this one, and then our new one point to the one that we figured out it would be smaller than. And this way, it both lets us cut down on the insertion time because we don't always have to go to the end every single time, and also allows us to keep track of a sorted list without having to do an actual sorting algorithm. So we don't need to do the original population of our data structure separate from the sorting, which we would normally do afterwards, similar to how we might have done in CS135, where you read everything first and then sort it later. This is also easier to do in a linked list than an array, because if you kind of consider the way arrays work, you need to shift everything over because they're located next to each other. So this is another advantage of a linked list in a specific scenario where you may want to use it over an array, is if you know you want things sorted and you're going to be receiving them in an online manner, meaning you're going to get them more and more over the course of the program, then you probably want to use a linked list versus a array. And the last topic we covered before the exam were stacks and queues. So we introduced these two new data structures, stacks and queues. And the stack was an example of something that is last in, first out, or LIFO, meaning that the last thing we added to it is going to be the first thing that we remove it from it. And then a queue was an example of a first in, first out style data structure. Let's do an example of a queue first. Queues, we said, were kind of like lines that you would experience in real life in maybe a store or in, like an amusement park or any place where people generally line up. Usually when you get into a line, you go to the back, and the first person who got there is the first one who is going to be served. Same thing with a queue, which is why it's called first in, first out. The first thing that arrived is the first thing that got there. So if we say we have three objects, A, B, and C, and the order that they arrive is A, then B, then C, then the way they leave or depart, well, I guess we'll say, is in the exact same order that they showed up. Right? If you have like a cashier here, and this is a checkout at a store, if A gets here first, then B gets here second, and C gets behind them, the new person always goes to the back of the queue, and the front of the queue is always where the next person is served from. The cashier always gets the person at the front of the line, not the person at the back of the line. So this is where that first in, first out comes into play. The other thing we noted about queues was that the order of arrival and the order of departure, when we insert and remove from this data structure, it doesn't actually matter that the order that the insert and the remove are matched in. The order is always going to be the same. So what I mean by that is if somebody got to the store, like we have this scenario where A, B, and C all show up, like just maybe seconds after each other. The order that they're going to be served in is A because they're at the front of the line, then B, then C, right? If I had another scenario where A and B show up, then the cashier serves them both, and then C finally shows up maybe 10 minutes later and then is served, the order that they were served in is still A, B, and C. Therefore, no matter the order that we do the insertion and the removal in, we would still get the same thing. And so as an example, let's do that down here. Remember that the insertion for a queue was called on queuing. So if I did on queue A, and then if you don't mind, I'm just going to keep using E for this, just so I don't have to write as much. So if I did A, B, and then C show up, And then if you remember, the way that we say leaving in a queue is called dequeuing, which is void and returns the thing that just, or sorry, is not void. It takes no parameters and returns the thing that is at the front of the queue. So we do 3 on queues and 3 dequeues. They're matched in that regard. A enters here and A leaves here, B enters here, B leaves there, and C enters and C leaves there. That's what I mean by matched, is that they both enter and exit the system. Then the order that these leave will be A, then B, then C, right? A leaves right here, B leaves right here, and C leaves right there. And if I did this in a different order, where I on queue A, on queue B, DQ, DQ, on queue C, and DQ, C, B, and A, then my order that they are DQ'd in is still the same, right? A gets DQ'd first, B gets DQ'd second, and C gets DQ'd third. You'll notice that we've rearranged these same lines of code. They're still matched, but the order that the objects leave the system is still consistent. It's still A, B, and C, and this would go for any sort of order that we do in a queue, because the first person that gets there is also always going to be the first one that leaves. This isn't the same in a stack, if you recall. So a stack was a last in, first out sort of data structure. So if we had arrival, A, B, and then C, and then departure, we want to measure that. And the way we set a stack works, right, is that we keep some sort of pointer to the top, whether that be an actual pointer or just an integer that represents it. And then every time we do an insert, we put a new object onto the top of the stack. So if it's just empty, then we're putting it at the bottom. So we first put A into our stack, and then B next, and then C last, right? And we keep track of the top at every given point. So after adding B, it would be on top of B, and after adding C, it would be on top of C. And then whenever we do a removal from this data structure, we also always remove from the top. Remember, this is called a LIFO data structure, last in, first out. So the last thing that just arrived is going to be the first thing we remove. And we said this was kind of like stacking things in real life. If you try to remove something at the bottom of the stack or middle of the stack, it's going to fall over. So you always want to remove from the top of it in order to keep the data structure the same, right? Or consistent. So we remove C first, then B second, and then A last. So if we do a straight thing where we just put A, B, and C into the stack and then remove them one right after another, then it's going to be exactly reversed. So a queue always does things in the same order that it was in the arrival, and a stack, if you kind of condense everything into the same location, is going to do it in reverse. Now remember that this is not always the case with a stack. Let's say we have another example down here. So remember that we have 2 operations, again, insert and removal, just like we have for a queue, but they have different names here. Pushing, it was inserting into a stack. So let's say we push A, B, and C, and then right afterwards we pop all 3 right in a row. Then the order of arrival here is still A, B, C, which we're going to keep constant. And the order of leaving will be C, B, and A. Right, so this one matches with that one matches with that one matches with that one. Right, the pop goes to the last push that happened. However, if we change the order of this code around a little bit, so let's write it in a similar way to how we just did with that queue, where we move 2 pops right after we do the pushes, and then we push C after that popping is done, and then do it here. So we push A, push B, push C. So same code, right? Different order. Then the order of leaving the system is different than if we had put the pops the way we originally did. Consider it's going to pop B first because that's the last thing pushed at this specific moment. Then it will pop A, which was the last thing pushed that was not been popped yet, and then this pushes in C and pops C. So the order of arrival here for both is A, B, C, but the order of leaving the system or leaving the data structure is BAC for a stack versus CBA, exactly reversed. So that was the main difference in terms of how we can use a stack versus a queue, is that it's not always just straight reversed. We can do things that are kind of just keeping track of historical data. So let's do one quick example just as a reminder of that, is that a stack is generally good for keeping historical information or just information about what has happened recently. So the example I gave the other day in class was, let's say you log on to a browser like Chrome or Edge or Firefox. You go to your home page, and from your home page you go to the Google page, Google homepage, and then from the Google homepage you search for the word computer science. So you do a query for the word computer science. You click on the first link and go to the Wikipedia page for computer science, and then you decide that you're done reading that. So you go ahead and hit the back button, which is going to pull you back to the query page for computer science, and then you click on the second link, which takes you to Stack Overflow. And then you just go all the way back to your home page. You hit the back button 1, 2, 3 times. And something to consider is that if you hit the back key, you are not going to have gone back to the Wikipedia page at any point because you've already gone back to it one time, right? So this keeps some sort of history about the information in which you browsed these pages. If we did this as a stack, then what we might do is we said for visiting, that would be pushing it onto the stack. So we first visit the home page, then we visit the Google page, then we visit the query page for computer science, then we go to the Wikipedia page for computer science, then we leave that page. So if you hit the back button, that's popping from the stack, and then we push the Stack Overflow page, which is where we went after we went back to the query page, right? So we kind of look at the stack for that. We first go to the home page, then the Google page, and the query page, and the Wikipedia page. We leave the Wikipedia page, so at this moment when we're at the Wikipedia page, that's where the top is always pointing to, is the thing underneath it is the page we're currently on. Once we go back one, we end up back here. Remember that the way stacks generally work is that they actually don't literally remove this thing from memory by deleting it, that they actually just move the pointer back down. And we do that to save time because remember that deleting things or deallocating things takes extra time. So this is, if you're doing an array implementation, you generally want to not do any sort of deletion, just do a lazy delete, it's called, where you just ignore the thing for now. So anyways, by moving this from the Wikipedia page, hitting the back button and going back down one page, if we access a new page like Stack Overflow, that replaces whatever was on top before, or like in this position. So the new top becomes Stack Overflow, and that's the page we end on. And then I think we said we would pop until we're done, right? So remember, the array-based implementation of a stack, we generally do some sort of overray. So let's say I pop until we're done here. Then again, just remember that this is not always the opposite order that we saw things in, right? The first page we went back from was the Wikipedia, then the Stack Overflow, then the query page, and then the Google page, and then the home page if we were to keep popping here. Right, so it's not in the exact reverse order. Notice that this is WSQGH, and it was HGQ. So the order we visited these pages in was HGQ, W for Wikipedia, and then S for Stack Overflow from the time you started this browsing session to the time it ended. But the order that these things were popped from the stack was like this: Wikipedia, then you hit back on the Stack Overflow page, the query page, the or sorry, not the query page, the the query page, the Google page, and then the home page. I'm sorry, I was right the first time. Notice that these two parts are reversed, but where we start to mix up the push and the pop order, that we don't necessarily get the exact same part reversed as well. Right? So it's not always exactly reverse. It's just keeps some sort of historical data about the thing you're trying to keep, which allows us to do things like backtrack. In the case of this, or backtrack, like if you've done the extra credit assignment, where it allows you to backtrack along a path that you're taking from one city to another. We can use this for any sort of thing where we need to keep track of some sort of history, and if we need to fix a mistake or something is wrong with our stack, we can back up. Or if we need to go back in not necessarily time, but to a previous state, which is kind of what the actual stack does for your functions. If you remember, like you've seen Stack Overflow as an error maybe in your programs, that's what that means, is functions are getting put onto the stack and they're getting popped as we need to go back to another function. So these were our two main data structures, stacks and queues. Queues being used for things that need to go in the exact same order that they arrived in, things like lines or just scheduling things in the exact same order that they are arrived in, whereas stacks are used for historical information. The last thing we should talk about is the two implementations of these. So let's first do the stack implementation, which is fairly simple for both implementations. These are commonly done with either arrays or linked lists, or some combination, like you might have seen in assignment 10, where you can more efficiently manage the space and also get some advantage of the array aspect of it. So let's first do the array implementation. You generally allocate some array in advance, and then we keep track of the top. So by default, the top is going to be at the beginning at position 0. And then all we do whenever we want to insert something into this is we simply put that object at the top and then update the top to point to the next thing. So the insert, really simple, just 2 lines of code. Store the thing into the array and then do top ++ to make it go to the next location. Really as easy as that. The disadvantages of this, like anything with an array, is that you might run out of space at some point, but we accept that just for the fact that it's a lot faster and easier to do than linked list. And then for popping, it's also pretty easy. All you do is keep a temporary variable to this thing, and move it back. Actually, I guess you don't even need the temporary variable. We just move it back and then return the thing that came after it. Right? So really, 2 lines of code for push and 2 lines of code for pop. They really are that simple. And then as far as our linked list version of this goes, like with any linked list, we keep track of a head, which points to null. In this case, the head we could also say is the top. They're the same thing, so I'll just call it top here. Let me actually move it over a little bit so we have some room. And this points to whatever is in the list. So again, by default, it's going to be null. Whenever we insert something, we simply put that thing at the top, put the data there, have it point to whatever the previous top was. So if it's the first thing in there, the previous top was null, hence this ends up with null. And whenever we do further inserts, rather than adding at the end, we simply add at the beginning. So I would go here, make a new node, have it point to the old top, which is this one, and then update the top to that. So a little bit more code than the array, although still not particularly crazy. We just need to make a new node, redirect it to point to the top, and then update the top. So really just 3 lines of code about, maybe setting the values if you don't have a constructor. And then the popping part is just that we simply have to point to whatever came after our current top so that we redirect the top there. Keep some sort of temporary variable to that value and then return it. So we would return this D1. So again, maybe like 3-4 lines of code, not particularly complex. A stack is honestly pretty easy to implement in both cases where we do it in these simple ways. Right? And there's basically no special cases in these either, right? We don't have to keep track of a separate head pointer, and we always add to the head, so we don't need to keep track of when it's null or anything. The only exception to that would be if you were trying to pop and it's null, maybe that's a good thing to check for, just so you're not trying to remove something from something that's empty. That's our stack implementation. It's relatively simple. We also have our queue implementations with both an array and a linked list. So an array implementation is essentially what you did for assignment 7 with that ring buffer. A ring buffer is the common way to implement a queue with an array. So we said there are 2 things to focus on in the queue, which are the front and the back. By default, we usually keep track of where the front is and the back is, and they're the same place, which is up here at the very beginning of our array. And then for our insertion, we said that what we do is we insert at the front, and then we update the front so that it points to the next place to be inserting into things. So if I want to insert D0, then D1, we would simply insert them both one right after the other. And then whenever we want to dequeue, we remove from the back of the line. Or I'm sorry, I probably should have flipped these, because that's kind of not how a line works in real life, right? Generally, the front is where the person removes from, and the back is where new people arrive or new objects arrive. So we would write at the back, wherever the back pointer is, and then continue to update the thing. And these could be actual pointers, or they could just be integers that index into the array, which is how I like to do it because I think it's easier, even though you may have done it differently in assignment 7. And then, sorry, for the dequeuing portion, we would remove from the front and increment. So the first person who got here is D0, so they're the first one to leave as well. And then as we insert into this, so if we inserted there, and then there, and then there, if we ever get to a point where we've reached the end of the array, if you're doing this with a integer index, then it's pretty simple. You just modulo, right, by the size. So presumably we keep track of the size of the array, which is 5 here, and just have it point back to the beginning once we hit the end, i.e. when it hits the size amount, we just modulo by size. Pretty simple if we do it with an integer implementation. And then we do have a unique scenario where if we were to, let's just say, insert one more thing to the back, perhaps I should do that from the other side so it's more readable. So if I had gone and inserted D2 here, D3 here, D4 here, and then D5 overwriting that one that used to be there, then we note that the front and the back end up in the same place, and we never want the back to lap the front and end up like going past it because that causes some issues. So we usually either reallocate or just prevent anything from entering the queue at that point and just say there's a cap on the amount of things that enter the queue. So the reason why this is important is because the front and back pointers are in the same place, both when the array is empty, which was our starting case, right? They both started at the beginning, And the same thing would go if you had unqueued everybody and then dequeued all of the things from the array, then this would happen as well. But it also happens when the array is full because the front and the back end up in the same place. So you can either check if the pointers are the same and keep some sort of Boolean that tracks those like a sizeof, or better yet, simply just keep track with a count, increment it when you insert, do it an onqueue, and then decrement when you do a dequeue. Right. And then it's just super simple to check. You just say, well, if the size is equal to the count, then we know that the thing is full. If the count is 0, then we know that the thing is empty. So I personally think that's the easiest way to do this. And then how you do extra things is just kind of up to you. So that one's a lot trickier than the stack implementation, despite how simple, I guess, the data structure seems in comparison. The linked list implementation is potentially a little bit easier, though. Again, we keep 2 pointers for the front and the back of the queue. By default, those are both going to point to null since it's empty. And really, these are just the same as a head and a tail pointer that we discussed earlier. So by default, it's going to point to null. When we go in and insert something, then both the front and the back are going to point to it. So we have one special case, which is where we are deleting from the, we're inserting into the position when nothing is there, when it's empty, in which case we need to set both of these. We put the thing into the queue, and then as we insert things into the back, as we did with a queue, and as you would expect to do with a line. Anything new that shows up goes to the back of that queue. And so here, this is the back. We simply make a new object or a new node, have it point to null, and we insert it at the back. So the back pointer goes here, and then we update the back to point to that new object we have. And we continue to do that as we insert more things, right? So here we create a new node, make the back point to it, make the previous back point to this new node that we've created, and so on and so forth, right? And this is nice because we don't have to worry about running out of space. We don't have any extra things to check because we don't need to check if the front and the back are equal to know if it's empty or full, because there is no such thing as full until you just run out of memory and your program crashes. So it's a little bit easier, I would say, than the array implementation, although again, it does come with those disadvantages of being a little less fast in terms of hardware implementation. But we don't need to do a traversal every time, right? So this is a decent implementation, or a decent use of a linked list, where because we're not constantly doing some sort of insert at the end, and because of the way that the data structure works, a linked list is actually pretty good for this. Okay, and so then if this is our onqueuing, we go to the back and add a new thing there. And again, dequeuing means you go to the front and remove whatever is there. So if we're dequeuing, we would keep a reference to this thing, make the front point to the next thing that's in the line, in the queue, and then return this object. And then deallocate, I suppose, as well, before we return. So the operations when doing this are potentially easier when we do a linked list versus a array-based implementation of queue. Okay, so that's all the new topics that we had covered for after exam 1 and 2. I encourage you to go back and rewatch the other review sessions because we basically just did the same thing. I think the only extra topic that I had mentioned, because I saw one question, which there's a very small chance you'll get it, but just in case you need to see it, was about the sizeof operator. So the sizeof operator is mostly for C. It's not so much a C++ thing, but it tells you how big a specific data type is. So this argument here is not a variable, it's a type. Integer is a type. Let's just say character is a type. And it just tells you how many bytes these things take up. So on a modern machine, this would be 4 bytes, and this would return a 1. This is useful for the main way this is useful is for changes in architecture over time or hardware. basically, if you had a computer in the 70s or 80s, an integer probably didn't take up 4 bytes because their memory space was a lot smaller. So just to save on space, an integer might have been smaller, like 2 bytes. And maybe in the future, an integer will be 8 bytes if we get really huge memory spaces for computers, right? So that could potentially happen at some point. Who knows? And it also allows you to figure out the size of custom types. So say I had a class here that I declared, EX, that had a character called C and an integer called N. Then if I asked for the size of EX, this would tell me 5 because it's made out of a character, which is 1, and an integer, which is 4, so in total it takes up 5. Just remember that when you do allocations of custom classes or user-defined classes, then it stores everything right after each other. So we did C first, and then N. C would be the first thing here, and then N would take up the remaining 4 blocks after that, for a total of 5. This also comes into play if you're doing weird pointer arithmetic stuff, if you know that everything's going to come right after each other. Now there are exceptions to this that make it a little bit weird, like strings or just general pointers, so maybe that's something to consider. But this is maybe something to keep in your mind. So that's the main advantage of using sizeof as an operator. It just tells you how much space that thing takes up. It doesn't affect us too much in C++. I do want to at least mention it, since I did see the one question. And I also wanted to mention it because I see a common mistake between students, which is that they try to use the sizeof operator to get an array size. I recommend instead using it just a separate variable for length and never doing that. One, because you have to compute it over and over again, which just takes time. But 2, because if you do dynamic arrays where you implement it with a pointer, it's not going to give you the size of the array because it actually can't know that. It's going to give you the size of the pointer instead, and even if you dereference it, it's going to give you the size of the thing being pointed to, which is not an array but an object. So try not to use sizeof for things like length unless you're doing static arrays, which are the ones from CS135, but in that case you should probably just have a constant anyways. So generally, even if you see this on Stack Overflow, please don't try to use it to get the length. It's really not as helpful as you might think it is. You can still do some crazy things with it, I guess, with pointers, but just general suggestion. The other reason these come into play, which we barely covered in this class because it's C related rather than C++, is for malloc free. I guess more malloc than free. Rather than using the word new and delete, if you ever write C, which you may at some point in your life, then the new keyword is instead done with a function called call malloc, and rather than doing something like this where you say new whatever type and then 4, you need to do malloc of how many bytes you want. So this is where sizeof is usually pretty helpful. So if I want to do an integer array that had 4 things in it, I would get however big a integer is on this system times 4, and then that's going to allocate 4 integers right next to each other. The malloc here standing for memory allocation, and then free just takes a pointer and deletes that stuff. Right? So that's just essentially the C syntax for the same C++ code that we're used to. Okay, so I think that covers about everything that we talked about over the previous 2 lectures that got cut off. One last note, I guess 2 last notes I had. One was about the threading lecture that I did before. I think I gave a bad example for race conditions. We were talking about threads which run simultaneously, and I said if you have 2 threads, so we make like thread 1 and thread 2, and we do the full declaration for it, which I'll just keep brief, do all this stuff. Then I think I said something like this, where if you access the same variable, we said something like thread 1 returned a variable sum1 and thread 2 returned some variable sum2, like the results of adding things they both did separately and concurrently, that this might cause race conditions, but I don't think this was a good example. Instead, you would expect these to be not like right after the threads, but in the code that they share. So if these two threads both ran on something called foo, like a function foo, and it had access to the same variable x that's global, then if I do some code and then do x plus equals sum, then if thread 1 and thread 2 both go and execute this code, what might happen is they'll both go and try to write to the variable x at the same time. Since there's an equal here, that means to write to it to like change the value of that variable. If they both happen to get there at the same time or about the same time and don't have information about what the other thread is doing, then they're both going to try to write to this, which is bad. So like if thread 1 found a sum to be 10 and thread 2 found the sum to be 12, then if this started out 0, thread 1 might go and write it to be 10, and then thread 2, if it tries to get there at about the same time, but maybe just like a clock cycle too late, or one clock cycle afterwards, it might then have already read this as 0 and made it 12. This is talked about in more detail in the classes that actually do threading, but I wanted to correct myself because I think I gave a bad example for this. You expect race conditions to be in a place where they share code rather than just right afterwards. I think that's the problem. Now the last thing I want to talk about was makefiles. I noticed that the assignment 10 had a makefile, so I just briefly wanted to go over the basics of makefiles since I didn't really talk about that previously. I'm not an expert on makefiles. I don't make them too often, but I at least want to share with you enough to at least get through assignment 10. Okay. So I have here two makefiles from previous assignments, assignment 8 and assignment 5. I recommend if you're going to make one for assignment 10 that you just go grab the assignment 8 one because I think it's pretty simple to modify. So let's take a look at that one. What you have when you do a makefile is at the top you have macros. These are just like variables essentially, but that get copy and pasted in for the places that they're used. So if I make a variable with this string main.o, anywhere that you use $ parentheses objs, it's going to replace that with the same text, is what those mean. And then we have some number of things called targets. So anything that's a name that you see here in black with a colon after it, then that's going to be a target. That means that if another target references it, or if you type that target when you type the make command, like if I typed make main, it will jump to that target and execute whatever code comes beneath it. By default, it will go for all. In this case, I don't know if it's consistently the tag all or if it's just the top one, but in this case it will be all because it is the top one, and it is the top one, so I'm not sure which one is which, but it will be all here if I just type make. What this does is after the target is first a dependency or a list of dependencies on the same line followed by some amount of code, which could be nothing like this one or as much code as you want. Here the dependency is main, which means that if this target is reached, it will go and jump to any targets it depends on. So here, if I do all, it's going to go to the target main. Main's dependencies are just main.o, so when the main target is executed, it's going to go to main.o, which is this target here, and then it's going to go to any dependencies here. Now these dependencies for main.o are not targets but files. Main.cpp was the main file here, and then it had some dependencies of headers that needed to be compiled with it, object.h and forest.h. The reason you would do this and list all these dependencies is so that it only recompiles things if it notices that it hasn't compiled it before and that the files that exist aren't newer than the compiled version. If it notices that they're newer, it will go and recompile any dependencies, is the reason you do this. So makefiles exist to try to optimize the way in which things are compiled and also make things easier, right? You don't have to type a whole bunch of compiler commands to do this. You just type make and it runs it, which is nice. So it has those two advantages. So this main.o target, it will go and say, all right, I need to go and update main.cpp, object.h, and force.h, which are going to get filled in there, and those need to be recompiled if they're older than those. Sorry, if main.o is older than any three of those dependent files. Right, so the target, the thing that you're trying to build, if that is older than these, then it's going to go and recompile this. Otherwise, it just skips this target altogether. Anyways, once it finds a target that is dependent on just files and not other targets, it will go and actually try to execute the code that comes underneath here. Again, we have macros, so cc, the compiler command is going to G++. The flags for the compiler, like the options for it, are these ones here, which just tell it a few pieces of information about error reporting and warning reporting and what version of C++ to use. And then it's going to compile main.cpp. Remember that when you do compile things, you just put the CPP files, the source files, not the header files. But the dependencies are there just to know what header files it was using anyways. So this goes, compiles it, finishes it, goes back up to here, which was the one that called it, and then does some linking. We haven't really talked about linking too much, but you have the option to, rather than compile directly to an executable like a.out, something that can be run, you do things that are kind of executable, but need to be joined with other parts to form a full piece of code. This doesn't really matter too much in this specific assignment, but if there's cases where you are writing a bunch of sub-programs, essentially, you only need to compile those individual parts as needed with like that whole things being out of date, and then put them together later by doing this linking step. So compiler can compile things, and it can also link things. The G++ here, because it's receiving this rather than a source file, a .cpp, it's receiving a .o, an object file. It's going to link those together rather than compile it. So this does G++. It does all the flags that we mentioned earlier. It has one additional flag, which, remember, the O stands for output, and it changes the name of the executable. By default, that's a.out. Here, if you do -o main, it's going to be main is going to be the name of the thing that's a program that you can run, and then all the things that need to be linked. Okay, so it links those together, and then that's the last target, since all is just referring to this one. So this essentially creates an object file out of main.cpp, depending on its headers that it had, and then links that to make a single executable, which the linking isn't really necessary here because we only have one thing, but it's just good practice. Then last we have this clean label, which is there to remove things. So you might recognize rm. That's a bash command that you normally do in a Unix-based system like Linux or Mac, and it just means remove all of these objects, which is just main.o. This is just here if you want to delete things. But the thing to note about this is that these commands that come after the target and the dependencies don't have to just be compiler commands. They can also be any sort of bash command. So things like rm, ls, cd, anything that you would normally write in the Linux command line works here as well. And that's why I brought up assignment 5's thing here. So you'll notice it first off compiles multiple object files, fish.o, main.o, tank.o, and then it links them all here since those are all the objects this is dependent on. This is also where the dependency for main comes. So this is nice because if you wrote all your code and then you realize that you have a bug just in the tank file but not in the fish file, if you rewrite the tank file and just change one function, it doesn't recompile main, tank, and fish. It just recompiles tank, I think we said was where the bug was. So for very big projects, this saves you time, and and so it's nice because of that. But the main reason, if we go back to what I was talking about, that I brought up the assignment 5 makefile is that you'll notice here that I also have a command that we usually don't cover in CS135 called echo that's available in bash. And all echo does is just tell you the same string you just told it and echoes it back to you, which seems kind of dumb, right? You just get the same string that you just said. But for scripts like this, it allows you to print things out to the person using your script, which is why it's here. So I have other bash commands that aren't just G++. And if you remember this assignment, it would tell you, hey, I'm compiling this. Then it would compile it and give you any sort of compiler messages. And then it doesn't check for whether it was successful or not, I guess. But it does just say, done, run this thing. So you can add extra commands. If you have things stored in another directory, you can do cd. You can create files if you need to touch or cat something. You have options to do any sort of bash command. Now, the last thing we should probably talk about is how this relates to assignment 10. You have to submit a makefile along with your code for that one. So if you want to make a makefile, I recommend using this one as a base and essentially just using 3 targets. So I recommend having a main, I guess you would want to call it reverse for the reverse program. And then you have 2 other programs that are for testing the stack and the queue. So I recommend having one called test queue and test stack, I think, are the executables for those. And then just simply change the O to be whatever those executable names should be. So for reverse.cpp, I think it's reverse, and then same thing for the other one. And then as far as your dependencies, just include the header files that correspond to those targets. So you probably want 3 targets at bare minimum, and then maybe the objects associated with those targets. So maybe 6 in total, and then all in clean. For the 3 source files that were provided for the 3 programs you need to write. Anyways, I think that about covers it for the review and the things that got lost in the previous 2 lectures. If you have any questions before the final exam, please send me an email or a message on Discord and we can talk about it. If not, best of luck on the final.